Alright, hello guys. I am back with that second two-dimensional example that I said I would be making in the previous video. Again, being a mechie, I really like the, physical kind of things. So this is a pretty simple 2-degree of freedom vibrations problem, right? We have this block with some mass m1 connected to a wall by some spring with a stiffness k and some damper with a damping coefficient c, right? There's a force acting on this block also. We're just going to keep it generalized with some f of t. And there's also a pendulum that's attached to this block with some mass m2 at the end. Okay, and I actually forgot to mention that this pendulum has some length L, right, from here to down here. All right. Now, we're interested in finding out, what's going on with the motion x and the motion theta. And actually, I've already derived the equations for you guys. And the reason why is that the derivation can be a bit involved. So if any of you people watching have not taken vibes yet, or have not gotten to multi-degree of freedoms yet, or anything of that nature, or even if you just don't want to see the derivation, you just want to see the Matlab portion, I've cut that whole part out. Right, if you want to see the derivation, you can. I've made a separate video for that. If it isn't up, it will be uploaded soon. But I just kept that separate because it will make this video longer than it really needs to be. The only purpose of that video is to show that these equations aren't being pulled out of thin air. They're real equations. They exist, and they aren't just random nonsense. I'll point out that these equations have been linearized about the equilibrium positions, x naught and theta naught, where both of those positions are 0. And we're also assuming that there are small oscillations or small vibrations, meaning that if we're looking at this pendulum here, it isn't swinging widely around here. It's just moving, ever so slightly back and forth. And that gives us freedom in how we can simplify the problem as well. Now, before I get started, I want to point out that I'm going to be making another video that is going to show how to solve the same exact problem, but faster. And the reason why I want to do that is, not too long ago, a person on YouTube reached out to me, commented on one of my videos, asking about faster ways to do this, and I realized that if you're handling any kind of system where you're dealing with equations of motion, and you have a large number of equations and a large number of degrees of freedom, and you want to do things in Matlab's ode45 solver, converting everything to state space can be a real drag. You'll see here x double dot and theta double dot appear in both equations, so this thing is highly coupled and will require a lot of substitution that's going on, and it gets even worse if you have, let's say, 10 equations or 20 or 30 or 40 equations. It can get really annoying. So the point of that video is to show you a quicker way. Note that it only works with linear multi-degree of freedom systems. So if it's nonlinear, we're back to the method that we're doing here, right? Maybe there are simplified ways of addressing nonlinear systems, but I'm not going to go into that in this video. So both that faster version video and the derivation video, their links will be in the description below. And for now, let's go ahead and continue ahead with doing things the normal way that I showed you guys previously. So here are our two equations of motion. I'm going to start working with the bottom equation first because it looks easier. I have a 0 over here. And so I'm going to solve for theta double dot. Alright, and if I solve for theta double dot, now we got a fairly simple equation. I'll have negative m2 L x double dot minus m2 g L theta, and that will be all over m2 L squared. Now, as you can see, there are m2 L's everywhere, so I'm actually going to simplify this equation a bit more, and it'll give me negative x double dot minus g theta over L. So this is a pretty good start. Things aren't too complicated. However, as we see, theta double dot is not in terms of all the lower order terms, and strictly the lower order terms, or functions of time, because it includes this x double dot term, which is the highest order derivative for x. So we're actually going to take this expression and substitute it into this expression in the first equation, which is lots of fun work. Not really fun though. So I have m1 plus m2 times x double dot plus m2 L theta double dot plus cx dot plus kx equals, okay, that was weird. Alright, equals f of t. And that x did not show up like it was supposed to. So let me take care of that. Alright. There we go. So this is the first equation that we had. We're going to substitute theta double dot into this guy. And if we do that and we simplify the equation, we're going to get m1 times x double dot minus m2g plus cx dot plus kx equals f of t. And it might seem a little bit hand wavy, so let's just go over that really quickly. Theta double dot is just negative x double dot minus g theta over L, right? So if I toss that into here, that L is going to cancel, okay? So that's going to leave me with m2 times negative x double dot minus g theta. That in turn will cause this m2x double dot to cancel with the m2x double dot that comes from substituting in the expression for theta double dot. But it will also leave me with the m2g theta term, and I left out the theta, my mistake. It'll leave me with this negative m2g theta term. So as you can see, this second term stayed in here after the cancellation of L, but the m2x double dot term got canceled out because this term is positive, okay? Just so that, you know, what I did makes sense. Now after that, we'll want to get x double dot in terms of the lower order terms, so let's solve for x double dot. That's going to give us f of t plus m2g theta minus cx dot minus kx all over m1, all over mass 1. Now this expression is actually very nice because it is in terms of all the lower order terms, right? Theta double dot does not appear in this expression, so this is the final expression that we're going to use for x double dot. And now we can substitute this back into this guy up here, so we can get theta double dot in terms of the lower order terms. Okay, so theta double dot, I'm going to rewrite the expression, is negative x double dot minus g theta over L. And if I substitute in this guy, that's going to give me negative f of t plus m2 g theta minus cx dot minus kx all over m1, and then all that minus g theta and over L. Now one thing that I'm going to do is multiply both the top and bottom of this expression by m1, just because, you know, the less fractions there are in an expression, the better, because keeping track of parentheses and such in Matlab is a very tedious task. So if I multiply the top and bottom by m1, I'll get this expression. I'll get negative f of t minus m2 g theta plus cx dot plus kx minus gm1 theta all over L times m1. And that's theta double dot. Circle this guy. Well, this is a box, but ignore that. Imagine it as a circle. Alright, so now we have the expression for theta double dot. We have the expression for x double dot. We had it earlier. I'm going to rewrite it again down here. It was f of t plus m2 g theta minus cx dot minus kx all over m1. So once again, we have our highest order derivatives. Okay, there we go. We have our highest order derivatives expressed in terms of our lower order terms, just like Matlab wants. Now, the one thing that I haven't done yet is set what the state variables are, so I'm going to go ahead and declare those. I usually do that last because I find it's just nicer to get the hard work out of the way first. So S is S1, S2, S3, S4. This is just the very easy work. And those guys are X and X dot, and also theta and theta dot, right? That in turn means that the derivative of our state vector, S dot, is just going to be equal to X dot, X double dot, theta dot, and theta double dot. Alright, we already know what these two guys are, right? From here we see X dot is just S2, and from this guy we see that theta dot is just S4, okay? And we have X double dot and theta double dot in terms of the lower order terms, okay? You usually see me substitute in these two expressions into the derivative of the state vector and then plug in the state variables, but I'm just going to go ahead and write the whole state variable format because you've already seen the expressions for both of these guys. So just keep track of, theta is S3, X is S1. Keep track of that when you see me writing out the final result for a derivative of our state vector. But let's go ahead and write that out. The derivative of our state vector, and I'm going to give me all the room that I want because this is the last part of the written portion. The derivative is going to be negative f of t minus m2 g s3, again that's theta, plus c s2, again that is x dot, plus ks1, s1 is x, minus m1 g s3, again s3 is theta, hopefully I'll have enough room for this, divided by L times M1. Alright, it's a really ugly L, but, not an L, it's a really ugly M, but it's an M. Alright, this is S4 dot, or theta double dot. Okay, then we have S4 down here. S4 is just theta dot. Alright, which we should know from here, if S4 dot is theta double dot, then S4 is theta dot, right? But anyway, next is S2 dot, which is also X double dot. Alright, and that expression is another large ugly thing. It's f of t plus m2 g s3. Again, s3 is theta, minus c s2. S2 is x dot, minus k s1. Again, s1 is x. I keep repeating myself, but I just want to make sure that that's clear since I didn't write out the full expression without state variables. And then finally at the top we have S2, which would be x dot, right? And let me make this clear also. This is the same as S3 dot. This is the same as S1 dot, okay? So this looks a bit sloppier than usual, sorry about that, but I really didn't want to write out a whole lot of stuff. In any case, this is the derivative of our state vector, so this is what we can plug into Matlab. So let's go ahead and do that. Alright, welcome to the Matlab portion of the video. Here, as usual, you'll see that I have 3 files for the 3 different kind of approaches that I talk about when I'm working with ODE45. This first file is for the mfile method, and remember that if you're using the mfile method that you need to call ODE45 somewhere else, whether it's in the command window, whether it's in another m file somewhere, you need to call ODE45 somewhere else. Additionally, you'll need to make sure that when you call ODE45, the function that returns s dot that you're referencing needs to be in the same directory or folder that you're in. That's just something important to keep track of. The second method is the function method. Here's the code for that. Again, if you want to see all the code, more slowly, you can just pause the video and take notes or take pictures as you need to. And over here, you'll see that the function handle method hasn't been written yet, and that's because I'm actually going to write that out myself in this video. You'll notice that I've already given the declarations for the various parameters. So the masses, stiffness, so on and so forth, all of that's been declared already. Notice the units also, and make sure that when you're doing declarations and you're, using ODE45, that the function that returns s dot has access to these declarations. Okay, so you'll notice that here in the mfile method, I've declared these guys right here inside the function. Over here in the function method, I go down to the function that returns s dot, and I declare the various parameters in here, alright? This is especially important for the function method, because if these guys were not declared in here, and were instead declared up here in the primary function, which is separate, but in the same m file, then this function would not have access to those parameters, and Matlab would get really confused wondering what in the world these various variables are, alright? So just be very careful with your declarations when you're doing them. Another approach, I guess, would be to use global variables, but usually that's frowned upon unless there's a clearly advantageous, reason for doing it. And then over here is the function handle method. So let's go ahead and start it. So let's start with the initial conditions. I have x naught as 0 meters, initial velocity as 0 meters per second, initial theta as 0 radians, and initial omega as 0 radians per second. And you notice that I stress the radians. The radians are important. As I mentioned, when I got those linearized equations, I linearized them about the equilibrium positions, and I assumed a small angle, a small theta. When you're making these small angle assumptions where things like sine theta become theta, you need to make sure that you're using radians, alright? Radians, not degrees. Just want to make sure that's clear when I'm doing this and when we get our results. And here are our initial conditions. Here's our initial conditions vector. You could declare this stuff a different way. I just like to have it this way for nice order. Initial time will be 0 seconds, final time I'll make 30 seconds, and the time span is obviously the initial time and the final time. And then I'll need to declare s dot as some general function of time and my state variables. So let's do that. As I said, I'm using a function handle. The first part of the derivative of our state vector is s2. And the next part is f of t plus m2 times g times s3 minus c times s2 minus k times s1, all divided by m1. The next part is just s4, and the last part is another long expression. Alright, and all that is divided by L times M1. Now before progressing, I want to point a few things out. First of all, for people who are used to MATLAB and who are used to declaring vectors, you might be wondering, if I'm hitting enter, why am I using these semicolons to make column vectors? Do you really need that? And the answer is no, I don't need this. I could remove these and MATLAB would not change its results at all because I've hit enter and knows that I'm making a column vector. So the semicolons are indeed redundant, but it's just a habit that I've built, I guess. Another thing that I want to point out is this thing over here. Be very careful when you're doing multiplication and especially division in MATLAB. These parentheses are necessary. Sometimes people forget them. If I were to write this out, if you write this by hand, a person might think, okay, this means this long expression divided by the product of L and mass 1. But when MATLAB sees this, it sees this whole entire expression divided by L and then multiplied by M1, which is not what you want. This is equivalent to putting M1 in the numerator. Okay? This is not what we want. You want it to divide this entire term by the product of L and M1. So just be very careful with these parentheses here. Just make sure you're using them correctly. And lastly, you'll notice that I use brackets here. If you use brackets like this, you'll notice that MATLAB will say, hey, you don't need the brackets, you can just use parentheses to group things together. It's really up to you. I did the same thing in the other pieces of code as well, as you can see. And it's really up to you. Technically, I guess you could consider it more optimal. Maybe MATLAB thinks it's more optimal to use parentheses instead. And so you can always change brackets to parentheses, after you've done this, if you want to. I just like to do it this way so that I don't mix up parentheses and such. I know MATLAB has a way for you to identify, where parentheses are opening and closing, but I like interchanging parentheses and brackets to help me keep clear track of the various items that I'm grouping together. But those are just some programming comments. Let's go ahead and continue with the numerical integration, and let's call ODE45. So ODE45, S dot is my ODE fun. I have tspan, I have the initial conditions, and then I'm going to extract with the values. So the x positions are in state values, column 1. My spelling. Okay, there we go. Those are my velocity values. Here are my theta values. And then my omega values. And you'll see me using omega because omega is often used, specifically little omega, is often used for angular velocity. And if anyone's curious about it or has forgotten, the reason why I'm extracting them this way in this order, like x is for column 1, v is for column 2, so on and so forth, is that it's just how we set up our state vector. And so this corresponds to the way we set up our state vector. If we set it up differently, we would call these guys differently, but we would get the same numerical answers ultimately. And now to see our results, let's go ahead and plot some stuff. I'm going to plot the displacements specifically. I want to point out that it's extremely important if you're using these things like small angle assumptions or small oscillation assumptions. It's extremely important that you check your results, because if you get your results and your oscillations aren't actually small, then that means that your assumption is incorrect. And if your assumption is incorrect, then you have some changing you need to do. You'll have to go back to perhaps nonlinear equations, and that's not fun. But it's important to check your results to make sure that they make sense and that the assumptions that you've made actually hold out in the simulation itself. Otherwise, you'll have to do different approaches or revisit the problem. Again, I want to reiterate, theta is in radians, not degrees, because of the assumption that we made. And for anyone who's wondering about it or is unfamiliar with it, this backslash here that I'm using, it allows me to see the actual Greek symbol theta when I'm putting up the title, as opposed to seeing, theta, like the actual letters. So that's much nicer. Let's bring this function to an end, and then let's call it. Here are the results. And as you can see, these angular displacements, these thetas over time, they don't get very large. And so our assumption about small angles is valid. We also see that the x displacements are pretty small too. So we can consider our simulation pretty accurate for the physical system that we are working with. Over here, I'm also just going to go ahead and plot the angular velocities. So that would be omega. And that's radians per second. And the reason why I'm doing that is just to, further validate the assumptions that we made. You won't really see the significance of this in this video. You'll see it more clearly if you decide to look at the derivation video. But one thing that we did with the linearization was if we saw terms like theta dot squared, or which would be equivalent to omega squared, or we saw multiplication with some theta dot and some theta, that no, I don't want that. Whoops, sorry guys. Let me run this again. Okay. If we saw terms like that, then we decided to cancel things out. So in the derivation video, there's some term that had like theta dot squared times theta, and if we were to do that calculation mathematically, we'll see that multiplying this stuff through, you get a very, very, very small value, and that makes it rather insignificant compared to the total problem that we're working with. So that's the importance of making assumptions when you're linearizing things. These plots further validate our assumptions, so we're good. And again, we can have confidence in our simulation. So hopefully this video was helpful. You can look at the other videos if you want to, the derivation video or the video that shows you how to get this done a bit quicker. And hopefully this stuff has been helpful to you. You can let me know in the comments down below, and thanks for watching.